Good day all, and thanks for being with us. My name is Alberto Montilla. I am co-founder and CEO at SPATIAM Corporation. And today, I'm going to talk to you about the evolution of communications and networking on the lunar surface. More specifically, how future users of the communication networks are going to be able to use mobile networks on the lunar surface that are connected to LunaNet. In order to do that, I'm going to present a DTN Network Function, which is a system that is able to connect mobile networks that are based on standards, 3GPP, and its users to LunaNet. We're going to do that through the following agenda. First, I'm going to present a brief introduction about Lunar Communications Networks, more specifically LunaNet. Then we're going to talk briefly about the Artemis 5 extravehicular activities, EVA plans, and how these plans include the use of mobile networks, more specifically 3GPP based mobile networks, as we know them as 4G or 5G networks. Then we're going to look at what it means to have a mobile network on the lunar surface in relation to the space networks, more specifically LunaNet. We're going to introduce then the concept of the DTN Network Function as a way to marry or to connect mobile networks on the lunar surface to LunaNet and its users. We're going to look at some initial prototype experiments and its results, and then we're going to end up with some conclusions and lessons learned for the audience. So let's start. LunaNet. LunaNet is the framework or the architecture for lunar communications networking and also for positioning, navigation, and timing, PNT. We're going to discuss LunaNet in the context of communications and networking, and we're going to leave PNT aside. As many of you may know already, LunaNet is a framework, an international framework, an international architecture that has been proposed and promoted by some of the key space agencies, including NASA, the European Space Agency, and the Japanese Aerospace Exploration Agency. And this framework is also supported by a large consortium of industrial partners as well, including SPATIAM Corporation. And what LunaNet enables is an open architecture to deliver networking at a scale. What that means is enabling the key communication services, starting from data transfer, but also handling things like science and emergency services in a way that it is open and standard. And the whole goal is to enable the creation of a lunar internet as the first step towards a solar system internet. Some of the key considerations of LunaNet includes the following. The first one is LunaNet, as any network similar to a terrestrial network on Earth, includes many users, and those are basically the users that are going to generate data. When you think about data, these data may be containing payloads that are hosted by a lander, they are hosted by a rover, or they are in a habitat, for example, humans in a habitat, or any other, in our specific case, as surface assets. What can generate data? Well, think about any sensor, any computer, any camera, any human for that matter. And then, in addition to the users, you have the network elements that have the responsibility to transfer or move this data across the network so that it successfully reaches the destination. When we think about the network elements in LunaNet, as many of you know, relay satellites play a critical role, considering the fact that both the moon and Earth are moving continuously, rotating for that matter, ground stations, and then in the specific case of surface communications, you may have surface network elements. For example, you may have network elements. So the way LunaNet is architected is there is a user segment and there is a network segment, very typical of network architectures. So now let's look at some of the key characteristics of LunaNet. Well, first is one of the big differences between LunaNet as a space network and the terrestrial networks is that LunaNet is expected to be highly scheduled. And the reason is very simple. First, assets are limited in nature, the number of ground stations that are available relative to the number of missions, access to those ground stations, the cost of those ground stations, and also the fact that line of sight might not be permanent. So that means that the link between, for example, a lunar relay and Earth may not be permanent. So in order to solve for all of that, LunaNet is expected to be highly scalable. What that means is that there are going to be contacts established between during a specific days and specific times for any mission. This is even more relevant when we think about the fact that most of the missions are expected to go to the South Pole of the moon, where in a 30-day cycle, it is expected that at least 15 days of those, there won't be direct line of sight. What that means is that there is the requirement to use a communication relay. Another key characteristic is because of the fact that it is going to be highly scheduled and there are going to be disruptions, delay tolerant networking is DTN, aka DTN is a key protocol stack that is required to ensure or guarantee the reliable transfer of data between two endpoints that are going through a highly scheduled, highly disrupted network. The third point is, as I mentioned before, the expectation is that LunaNet is going to be formed by multiple administrators. Think of different space agencies, industrial partners, other type of organizations. So the expectation, similar to the terrestrial internet, is that there are going to be multiple service providers serving LunaNet. And also there are going to be multiple users and multiple type of users. So users that requires high throughput, real time, because they are, for example, doing the streaming of media, audio or video, versus users that requires very low bandwidth and they have more delay tolerance, for example, IoT type of users. So fast forward to Artemis 5. Artemis 5 is the first mission, NASA mission, that plans for long-range extravehicular activities, formerly known or commonly known as EVA. In Artemis 5, the plan is that there is going to be a lunar terrain vehicle, it's a rover, to hosting two astronauts that are going to be at the South Pole of the moon during the Artemis 5 mission. And these EVAs are planned to go to an extended range, up to 10 kilometers from the HLS, from the Human Landing System. So basically it's going to be, the rover is going to be, and the astronauts are going to be far away from the landing sites. And each of these activities, each of these trips are going to take up to, have an autonomy of up to 8 hours. What are they going to do? Well, they're going to do, among many other things, as you may imagine, primarily science, and they expect to, as part of the activities, they have a key set of transmission requirements. For example, they want to transmit up to 4 simultaneous 4K video streams. 4K is also known as ultra high definition video. The concept of operations defines that each astronaut is going to have 2 cameras. One of the cameras is embedded in the helmet, and the other camera is going to be a handheld. In addition, it is expected that the LTV also have a camera. In terms of simultaneous transmission requirements, it's expected or desired that there are at least 4 simultaneous video streams that are basically streamed to Earth. In addition to that, high definition audio for communications internally between the astronauts, and also between the astronauts and the control center and the different users that are in the conference. In addition to that, the standard telemetry and commanding using standard CCSDS protocols to basically operate the different payloads. And imagine that, in this specific case, payloads may be, you can define payloads as the spacesuits and specific elements within the spacesuits, also the rover and specific elements to the rover. And in addition to that, have enough bandwidth to perform operations and maintenance on this surface equipment. That means, for example, if you have to upload a new software or you have to patch something or to change something as well. So those are the key requirements: for simultaneous video streams to Earth, support for HD audio, and then bandwidth for telemetry and commanding and operations and maintenance. One of the key innovation goals for NASA and its partners as we continue exploring the lunar surface is to upgrade the technologies used in the spacesuit, more specifically the communication technology used in the spacesuit, to technologies that support more mobility and also higher bandwidth to basically transmit multimedia and basically more data. And the specific goal is to upgrade the existing spacesuit UHF communication systems with standards-based mobile network technologies, more specifically 4G and 5G systems. And the reasons are very, very simple to explain. The first one is support of extended range. We know that by the use of mobile networks, basically you can expand the range pretty much in an unlimited fashion, starting with initial goals, as I explained before, of 10 kilometers, but then as you know, as you add more cells, then you can increase the coverage, right? The second part is the additional bandwidth for supporting multimedia transmissions and more bandwidth relative to the existing technologies. And something very important is to leverage the economies of scale. The terrestrial mobile networks, we are right now in 5G, 6G is in development. And if you look at the development over the last 40, 50 years in the mobile network has been, the bandwidth and the mobility support has been dramatically evolving thanks to the economies of scale. There are billions of users now that have a mobile phone in their hand, pretty much, getting closer to 100% penetration. So the space actors wants to leverage those technologies and be participants of the economies of scale. So with that, basically what you're gonna see is that, and again, I'm focused on Artemis 5 for the moment and that time frame where the expectation is that there is a mobile network station on the human landing system and there is a network station on the lunar terrain vehicle on the rover to extend the network coverage, and then the astronauts and any asset which is in the coverage area would benefit to from that coverage to transmit high bandwidth back to Earth as well. So basically you have a mobile network on the lunar surface, and now you have to transmit the data, for example, generated by the astronaut's video camera back to Earth. How do you do that? And it passes, or it goes through basically the integration of the mobile networks with LunaNet. And when we explore that integration, of course, there are some challenges. In addition to the benefits we just discussed, there are some challenges that comes with it. And those challenges are primarily related to the fact that mobile networks were created for the terrestrial use case. And mobile networks were also created primarily for the consumer. And when you look at that, there are some important difference or opportunities to highlight as well. So the first one is mobile networks by default has been designed for multiple access. That means that you have a radio link and multiple users can access the network through the same radio link. In the case of LunaNet, and more specifically on the surface part of the network, basically LunaNet relies on these technologies to implement multiple access. The second big difference is that the mobile networks, because they are basically built for terrestrial connectivity, it assumes that there is permanent network connectivity. What that means is that the base station is connected to the core network primarily, and to the internet primarily via cables, fiber optics, microwave links, which are basically operating 24/7. In the case of LunaNet, we know that the connectivity from the lunar surface to Earth is scheduled. What that means is that there are disruptions and the contact is not permanent. In addition to that, when you look at LunaNet, there is the additional aspects of the signal delay, as we know well, transmitting a let's say, a packet through radio frequency or to an optical link experience latency just because of the distance between the moon and Earth, and that latency is approximately 4 seconds of round trip time. And what that means is, in practical terms or technology terms, it means that for LunaNet, DTN, and more specifically the bundle protocol stack, is introduced as the networking layer to ensure the system is able to handle the latency or the additional delays and the disruption associated. Meanwhile, the mobile networks are only based on IP for the moment. So with these challenges, with the requirements around connecting mobile networks to LunaNets and the benefit that that's going to provide, we proposed basically a project to NASA, and that project was executed during the second half of 2024 and the first quarter of 2025. This project was completed in February 2025 by SPATIAM to propose a DTN network function. And the main purpose of the network function is to connect 4G and 5G mobile networks and its users through LunaNet, achieving that, for example, an astronaut that is behind a 3GPP system, it's able to send data, video streams, etc. to users, whether they are science users or mission operations users on Earth. So for that, we basically collected the requirements, the key requirements in terms of throughput. For example, we established that each user should be allowed or should be able to send data with a throughput of up to 100 megabit per second total per user, and from a system perspective, 1 gigabit per second. The system would be based on bundle protocol version 7 to support DTN, and the key applications would be telemetry and commanding, media streaming, and file transfer, also used as a backup for real-time connectivity. And something very important to highlight here is that these user applications would use standard protocols, whether they are standardized by CCSDS or IETF or 3GPP for that matter. And in addition to that, this same network function would be used as a conduit to perform operations and maintenance of the 3GPP systems itself. We established an overlay network. We call it the DTN Network Function LunaNet prototype network, where we set up the different nodes. We also set up the contact plan for the network. We perform the configuration of the nodes and then payload and application operation. We obtain some key results. The first one is we were able to create a network function to deliver 100 megabit per second per end user, in that case 2 astronauts and 1 rover, and a total of 1 gigabit per second as total throughput. This included the following data that transmitted simultaneously: 4 simultaneous 4K streams from the lunar surface to ground, 2 megabit per second per user for operations and maintenance, and for 500 or half a meg per second for basic telemetry and commanding. We created a fully managed network and payload operations, and we created that using a service provider architecture that is LunaNet compliant. We have a full demo available. So we performed not only the feasibility analysis, but we delivered a prototype for basically validating this approach. So with that, I want to say thank you for your time for listening to me today. Again, DTN Network Function as a way to connect 3GPP or connect mobile networks and its users on the lunar surface to LunaNet. It is possible, feasible, and we have a prototype available. We are looking forward to see the evolution towards Artemis 5 and the first EVAs, long-range EVAs that would enable that are enabled with high definition, ultra high definition video. It would be awesome to basically see that live once we get there. So with that, thank you very much, and let's stay in touch.